So I am going to assume, because I don't, I'm in this virtual environment, I can't see my audience, I can't poll the audience, so I'm going to assume that everybody knows nothing about ultrasound. And that's a great place to begin, is just with doing a little bit of education about what ultrasound is and what the characteristics of ultrasound are and how those characteristics are applied in our technology to enable us to have superhuman hearing, to hear all of these defects that can threaten our electrical assets. So just to just to get back to the point of the introduction. So SDT is a Belgian-based manufacturer of ultrasound technologies, but I'm based in Cobourg, Ontario, which is just up the road from Toronto, right along the shore of Lake Ontario. We are Ontario's feel-good town. Our reason for existing we're actually in business 50 years now, is to enable our customers to achieve their operational objectives by advancing the reliability of their assets. And that's a really large statement because I'll tell you, it's large because ultrasound does so many different condition monitoring and predictive maintenance related tasks. Now, this presentation is only going to focus on a singular task, which is electrical applications. But in getting to the point, I'm going to run through what we call the 8 application pillars. So everybody here in the audience will have a good idea of all the different ways that ultrasound can serve them in their condition monitoring and predictive maintenance goals and have more reliability in their plants. I like to begin by just going over the characteristics of sound, because that's what we're detecting. And there's really 3 classifications of sound. There's infrasound, audible sound, and ultrasound. Now, infrasound, we can't hear that. Sometimes we can feel it. That's really more for whales and elephants and maybe seismic sensors for detecting things like earthquakes and whatnot. Audible sound, well, that's my voice. That's the noise of the plant that you might work in. That's the traffic that we hear when we're on a busy street, or the music in a rock concert, or what have you. And then there's ultrasound, beyond 20 kilohertz, technically. And ultrasound refers to sounds that we cannot hear. They're above the range of human hearing. Now, there's 3 characteristics of sound that make it that explain to us why ultrasound is such a fantastic technology for finding all of the defects in our assets. But if you look at this slide, you'll see that we've basically drawn out the a sine wave or a sound wave to represent the wavelength of the different classifications of sound. And so what happens is, as we go higher in the frequency range, you can see very clearly that the wavelength gets shorter and shorter as we go higher in the ultrasonic range. And what that does for us, now how do I get rid of that? There we go. What that does for us is it gives us an idea of these classifications. So the first characteristic I want to talk about is distance. Oh, those lines don't go away with my slides, eh?
No, that's all right.
Well, I don't like them on there, but
Well,
let's see if I can clear them. There we go. When I do it in
yeah, there it
PowerPoint,
is.
when I do it in PowerPoint, they disappear as soon as I advance the slide. So I won't do that anymore. Actually, I'll use my pen. I love to draw things. There we go. I like that one better. So distance. Distance is the first characteristic that we need to understand when we're talking about ultrasound. Ultrasound needs a medium to travel through. So whether it's my voice producing the sound, or if it's the friction and rubbing and impacting in a bearing, or if you strike a string on a guitar or a piano, or if you have arcing and corona discharge in an electrical system, all of these things will produce sound, and that sound needs a medium to travel from its source to our ears, or from its source to, in the case of an ultrasonic detector to the sensor. And so distance plays a role. And if we look at infrasound, well, infrasound can travel hundreds of miles. It can travel through the earth, it can travel through water, and it travels a far distance. As again, shorter wavelength as we go higher in the frequency. So as we hit audible sound, you'll see that the distance that sound travels through its medium becomes shorter and shorter. And as we get to ultrasound, it gets even shorter. Well, this is an advantage for us because we're not only trying to detect the source of ultrasound, we're trying to pinpoint its location, especially if we're looking at a substation or if we're looking at high voltage transmission and distribution lines, or if we're trying to find sources of electrical problems inside switchgear cabinets. Trying to find them with audible sound or infrasound would be impractical, but ultrasound, because it travels that short distance, we can pinpoint its exact location. The second thing that allows us to pinpoint its exact location is direction. So, or what I like to say, directionality. And so if we take these three images on my screen here, you can see that infrasound, if the center dot here is representing the source of the sound, well, in a low frequency, it's going to radiate 360 degrees. Imagine throwing a pebble or a stone into a pond or a swimming pool of still water, and you have that ripple effect traveling in 360 degrees. Well, that's infrasound. Audible sound also is less directional. So if if I was in the audience right now and I was facing you, and here's the audience over here, and I'm speaking to you in this direction, the people standing behind me would tend not to be able to hear me as well as those people standing in front of me. And that's because the audible sound of my voice is a little bit more directional. Then as I go to ultrasound, we'll look at here, the direction that ultrasound wants to travel through the medium is about 60 degrees. I like to say, just imagine a flashlight beam. If you were walking through the woods at night with a flashlight beam, that beam path from the flashlight is very similar to the directionality of ultrasound traveling from source to sensor through the air. Well, this is advantageous for us again, because if we're trying to identify the source of a defect by the ultrasound it produces, well, we don't want it. We want to be able to pinpoint it quickly. So this directionality really helps us. The third characteristic we need to keep in mind is something we call boundary behaviors. And boundary behaviors refers to how well a sound moves from one medium to another. For example, if I'm at the bottom of a swimming pool and I yell, well, first of all, I'll probably drown, but the sound of my voice is going to travel through the water. But when it reaches the surface of the water, it's not going to pass from the water into the air, because sound doesn't like to transfer from one boundary to the next. Now, the lower the frequency, the better it is at doing that. Imagine you're pulling up to a stoplight and somebody pulls up beside you in their car and they've got a big subwoofer with a stereo and it's really blasting out that bass. Well, that bass is subsonic. It's very low frequency and it will travel through the steel of the car, through the air, through the steel of your car, and you'll actually feel it shaking your body. That's subsonic sound. But the ultrasonic sound doesn't like to move boundaries. So if ultrasound, for example, was produced by the rubbing and friction of the rolling element bearing, for example, well, that ultrasound wants to stay home inside that bearing. And so we don't really hear it that well with ultrasound. So this is a real advantage for us. And again, with this drawing, if this center diagram, the center of the diagram is my source of ultrasound, the ultrasound wants to radiate inside of this volume, but the only way I can get the ultrasound to transmit out of the volume is to use an ultrasonic sensor like this, and then it travels up my sound guide and my waveguide and into my detector. Well, this is also beneficial for us because if we're, for example, we're trying to listen for arcing or corona discharge partial discharge inside of an oil-filled transformer. Well, the way we're going to hear that is to put an ultrasonic sensor on the body of the transformer and pull that ultrasound out, just the way a doctor might put a stethoscope on your chest to listen to your heart or your lungs. We're putting a stethoscope on the outside of the transformer or of the asset to hear what's going on inside ultrasonically. Now, something really important and something very cool has to happen for us to be able to hear ultrasound, and it's called the heterodyne principle. The heterodyne principle is trigonometry that allows us to have superhuman hearing. This trigonometry takes signals that are happening in the ultrasonic range and it translates them to a frequency that we can hear in these noise attenuating headsets. So all of our ultrasonic detectors that we manufacture have this heterodyning filter in it, which allows us to have superhuman hearing. Our assets are speaking to us in a language that we don't always know or understand or can hear. The heterodyne principle is Google Translate for us asset managers so that we can take the pulse and really get an idea for the health of our assets. Ultrasound owns the apex of the P to F curve. Well, what does that mean? If you're familiar with the P to F curve, or what we call the P to F of the P to F interval, sorry. Well, the P to F interval is a way for us to diagram what the potential failure is and when the functional failure is going to happen. So the potential for failure happens after the design and the installation of an asset. And again, we could be talking about pumps, motors, gearboxes, transformers, switchgear, what have you. The day that you commission or start up an asset, the clock starts ticking on that asset to fail. And so what we want to do as condition monitoring and reliability engineers is equip ourselves with technologies that take this curve and flatten it out. The longer we can keep that P curve flat, the better job we're doing as reliability leaders. And so what we do by drawing this diagram is what I'm telling you is that ultrasound is the earliest, gives us the earliest indication that an asset's condition is changing. Long before vibration analysis, oil analysis, audible noise, before infrared thermography, before mechanical looseness, all of these other technologies are useful, and no one of them is better than the other, but ultrasound gives us the earliest indication. So it's kind of first, it owns the apex of the P to F curve. So understanding a little bit about sound and a little bit about the heterodyne and a little bit about where ultrasound fits in the P to F interval, the next question you want to ask is, well, where the heck can I use it? Well, we want our assets to be fit. That's our job as reliability technicians, is to create fit assets. When our assets are not fit, they give us symptoms of failure. And those symptoms of failure manifest themselves as friction, as impacting, or as turbulent flow. And so the first letter of each of those words forms a convenient acronym that we call FIT. And so just ask yourself this simple question. Is the defect I'm looking for producing friction, impacting, or turbulence? If the answer is yes, then ultrasound is the right technology for you to use to find that defect. Well, we talk about applications now. So we understand how ultrasound works and why ultrasound is advantageous for us. What we need to do is understand where we can use it. And the first application pillar that we talk about is leak detection. And so pretty much everything will leak, whether it's compressed air, SF6 gas, vacuum leaks. There's all kinds of areas where our plant will leak. Well, when things leak from a high pressure to a low pressure, it produces turbulent flow. And remember, turbulence is one of our three letters in FIT. So we can find pressure leaks and vacuum leaks. And what's key here is we can find them in noisy conditions. The background noise from our plants isn't a problem because our ultrasound detector is only tuned to 40 kilohertz. And those noisy things that we hear are down in our level of hearing. So ultrasound produces a filter to block them out. The next application pillar is lubrication. We want to avoid over and under lubrication of rolling element bearings. And when I don't have a good lubrication film in my bearings, what do I have? I have friction, and friction starts with F, and it's one of our three. It's one of our FIT symptoms. So lubrication is another great application for ultrasonic technology. The one we're going to spend the most time on is electrical. So let me jump past that one and get to the other ones. The fourth application pillar where we use ultrasound is to assess the tightness, the internal tightness of a valve. And so if I've got something flowing across this valve, it's going to produce T for turbulence. If it's producing turbulence, I can detect it with my detector. So if that valve is supposed to be closed and I hear turbulence across the head of the valve, I know I've got a problem. Just like a valve, we have steam traps. Steam traps are really just a valve with an IQ of 1. I like to refer to a steam trap as a toilet. Its job is to remove waste so that our boiler feed water can remain pure. So a steam trap's job is to sit there and collect condensate and then purge it from the system. Well, when a steam trap fails open, I'm going to have turbulence across the steam trap. When a steam trap is failed in the blocked position, I'll have no turbulence across the steam trap. I can also have mechanical failures that produce friction and impacting sounds. So there's lots of things I can do with ultrasound to diagnose the condition of my steam traps. Same thing for hydraulic systems, where I'm dealing now with flow or turbulence through the valves of the hydraulic system. I'm also listening for cavitation in the pumps. I'm listening to the bearings on the motors that are driving the pumps that are producing the hydraulic system pressure. And so lots of applications for troubleshooting hydraulics. And then finally, tightness testing. I can use ultrasound to determine the tightness of any kind of volume, whether it's a house, a car, a ship, as is the diagram here. I can also use ultrasound to check clean rooms in hospitals or in semiconductor plants, lots of places. So there's your 8 application pillars for ultrasound. And let me just diagram them all out for you. Mechanical, leaks, lubrication, electrical, valves, steam, hydraulics, and tightness. When we use ultrasound to take care of these 8 applications, we create a world where we have zero waste and zero unplanned downtime. When we have zero unplanned downtime, it means that our mechanics and our maintenance personnel can work without stress. They can work without the pressure of getting things back in a hurry. And when that happens, we have zero accidents and we have zero deaths on the job. Because let's face it, we all signed up to work, but we didn't sign up to get injured or get killed on the job. So I believe that ultrasound and condition monitoring in general leads to a safer workplace and it leads to a safer work culture. So let's get focused now. That was very general. I want to get focused now on electrical reliability tools, and we're going to look at some case studies. And you just let me know if I'm running a little bit long. I tend to not pace myself as well as I should sometimes. All right, I want to start just by talking about one of our solutions, which is known in industry as the SDT 340. And this is a handheld data collector, which has been on the market now for about 5 years. That's what it looks like. It's about the size of a big clunky remote control that you'd use for your television. The nice thing about that is that all 12 of these buttons are easily accessible with my thumb. So it's got a nice one-handed operation. You can see the color screen, high resolution on the color screen. It measures both ultrasound and vibration. So I can plug vibration sensors in here and do vibration analysis as well as ultrasonic analysis. It's portable. It's got its own battery pack. I can carry it around. The battery lasts about 10 hours. It's pretty lightweight as well. I can holster it on my belt or I can carry it around. UAS3 and UAS Lite, these are softwares that we built to do analysis of the data and to manage all of the assets that we have in our facilities. With that, we can use the 340 in survey mode and off survey mode. For electrical inspections, mostly I'm working in off survey mode. If I'm going to a substation, I'm just surveying the whole substation and listening for problems. The only where I would use it in survey mode would be if I'm going from electrical cabinet to electrical cabinet, and I'm listening inside those cabinets to hear if there's any corona or partial discharge going on inside the switchgear cabinets. And I would set up a route or a database of all of the switchgear cabinets in my facility, and I would log decibel levels. And if I have an alarm triggered, then I'd even take a time wave form or an FFT of what's going on inside that switchgear panel, so I can then go back to my software and do some analysis on it. I can do analysis on the screen, and I can also do analysis on my computer, and I can capture up to 256,000 samples per second, which basically just means that if the electrical fault that we're listening for is short in duration, there's zero chance that I'll miss it because I have so many lines of resolution, 256,000 measurements in 1 second. So I just want to show you, I got a picture here of a transformer. On the left, you'll see this is a screenshot from my software, and we took so this is a frequency reading. So what we've done is we've captured data from this transformer, and we're looking at it in the FFT spectrum, and we put a delta cursor of 50 hertz on here, and so we can see that each one of these repetition frequencies is equal to 50 hertz. What does that tell me? It means that the destructive corona that we picked up in this transformer is located somewhere in Europe or somewhere where the line frequency is 50 hertz and not 60 hertz. Let's have a listen. I don't know if... So I don't know how well you could hear that, but I could hear it very well in my headset. We picked that up in a very noisy facility. So all of the noise, the background noise was filtered out by our SDT340, and all we heard was that that destructive corona sound, and that's what you would expect to hear. Now here's a three-phase commercial transformer that's probably sending some power to this light duty commercial building over here. And again, we have 3 phases, and with the doors closed, we were able to hear through the air gaps in the doors, we were able to hear some buzzing sounds. But we didn't, so then we got permission to open the cabinet up, and from a safe distance, because we use a parabolic antenna that we can listen to from a safe distance away, well, we were able to figure out which of the 3 insulators was creating the problem. So this was the sound on the left insulator. Pretty quiet, really. I mean, you can see, and we just captured a 3-second signal, and you can see just this blue fuzzy line here. That's the signal, very, very low level. So then we went to the middle transformer, and this blue and fuzzy is getting a little bit bigger. Again, the same 3-second signal. If I just go back, you'll see on the original signal, our microvolts, or the energy that we were picking up with our ultrasound sensor, was maybe about 50 microvolts. Now we're up around 100, 175 microvolts. And it got a little bit louder. Then we moved and we pointed at the right insulator. So this is really just playing hot and cold, right? We were cold on the left, we were warmer in the middle, and we were hot when we pointed at the right. So now you can see the energy is up over 400, 500, and all of these lines here. Well, if we put this into the FFT, we would see that these are lining up with 60 hertz peaks. And let's have a listen. So non-intrusively and from a safe distance away, we were able to detect the presence of a problem, open up the doors, and say it's the insulator on the right. Now electrical maintenance can come and do their thing. A lot of times, this is again owning the apex of the P to F curve. While we're finding this problem very, very early in the failure curve. Um, this could be remediated just with a little dry ice cleaning. And a lot of times that's all this takes to get it back, because the corona discharge can be part of it can be created by a breakdown in the dielectric material, or it could be a loose fitting or a loose connection, but it can also be dirt. So if we clean away that dirt with a little dry ice, and we come back and inspect it again, and a lot of times that ultrasound signal has now gone quiet. So that's simple maintenance. And again, the earlier you detect something in the presentation that came before me talked a lot about predictive maintenance. Well, we're monitoring the condition here so that we can predict a failure. We can't predict exactly which day this insulator will fail, but because we got to it so early and we were able to remediate it with dry ice cleaning, well, it never really became an issue. And that really is the power of predictive maintenance, isn't it? We took that same signal now and we put it into our FFT, and again um, we saw 60 and 120 hertz peaks between each of these repetition frequencies. So we knew that it was corona. We knew it was part of the line frequency. Now here's an inspection that we did on a motor circuit control panel, and again outside. Uh, from just outside with the panel doors all closed, we were able to hear this problem right here. All right, so here we are. Here's our time waveform here. And we can see that we captured a 5-second signal. And we got a lot of activity going on here. It's buzzing and crackling. And if we look down here, we can see that again, each one of these peaks is correlating to 60, 120, 240. So this is definitely a 60 hertz line frequency. We know we've got some kind of a corona effect going on inside that switchgear panel. But the question is, where is it? Which one do we open up? Well, the easiest way to do this is to take a contact ultrasound sensor. Remember, when at the beginning, I spoke about using the way a doctor uses a stethoscope to listen to our chest and our lungs and our heart. Well, we're going to listen to the heart of this switchgear panel using the same methodology. We're going to put a magnetic contact probe on the panel, and we're going to take a decibel reading in the ultrasonic range to figure out where the loudest point's coming from. And so here we had 41 decibels. Here it got a little bit louder, 42 decibels. We got a little bit quieter as we moved away, 38, 36, 35. So if I come back to here, whoops, I went one too far. If I come back to here, I'm going to recommend that we start our search in this area right here. So we'll open these up, and then of course we're going to suit up and we're going to put our arc flash and our PPE on before we open this up. But once it's open, now we can do some infrared thermography. Maybe we'll find something, although heat is a little bit more later in the failure curve than ultrasound. But once it's open, again, from a safe distance, we can also listen and hopefully hear exactly where that buzzing corona discharge was coming from. Okay, the next product classification I want to talk to is something we call the SonaView. And SonaView, if we take the word sona, that's Latin for sound, and view is to view something, to look at something. And so what we're talking about here is acoustic imaging. Oh, excuse me, acoustic imaging cameras. I'm just going to stop here and take a quick sip of water. Thank you. So what is an acoustic imaging camera? Well, on the left here, our model is holding an acoustic imaging camera. It's a it's you can think of it in terms of an infrared camera because it looks like an infrared camera, but it doesn't measure temperature, it measures sound. On the front side of this, you'll see that there's a 112 ultrasonic digital MEMS sensors, and those MEMS sensors are focused on far distance sources of ultrasound. And when I mean far distance, well, we've detected things as far as 200 meters away. Now, one of the ideal uses for an acoustic imaging camera is in a substation. And you can see on the image here, we've got a three-phase transformer, and we're picking up ultrasonic noise at all three phases. Sorry, this one's kind of cut out, but you can still see it. So this little burst of color here, this little rainbow burst of color, is an indication of where air sources of airborne ultrasound are. And we can visually display them on a camera. And then if I just move my finger down and I hit this yellow button here, I can store that as a picture or I can store it as a video. We use acoustic imaging cameras for two primary applications. One is compressed air leak detection in your plant, and the second one is for uh, high voltage transmission and distribution lines. So, you know, those big power lines that are 600 kV running out of Darlington and Pickering and Bruce, and well, we can scan all along those lines and hear where line bushings might be losing some of their insulation properties. We can also safely inspect substations and the like. And from a safe distance, we can always be on the safe side of the fence with an acoustic imaging camera. So I want to talk about a really interesting application for that we use, and this is a dam that hydroelectric dam in Western United States. And one of my customers in Erie, Pennsylvania, what he does for a living is he goes around and tests different facilities for electrical integrity. And he was called in. They were doing a big rewind, and he was called in to do some testing and commissioning before they put this back into service. So here's a high pot that he used to do some of his testing. And I'm just going to move forward onto this. So here you can see, and this is I think it was something around 20 feet in diameter. So if I just go back a slide, this is a floor platform. So you can see back here, you can see the diameter. You can get an appreciation for the diameter of this asset. And it was all completely decommissioned and then rebuilt. And my friend Craig's job was to go over there and do a commissioning on it and make sure that it was rebuilt properly. So they had that high pot connected to it. They're running a super high voltage through this thing, and using his SonaView acoustic imaging camera, he isolated only one singular defect, and it was right there. He took a picture of it. He marked it off. They oh, I think that there's a slide missing. That's unfortunate. Yeah, there is a slide missing. Let me just get back to that and tell you, there's a slide here that shows what the defect was. In behind there, they found a welding rod. So during the rebuilding of this asset, one of the welders had carelessly discarded a welding rod, and it was caught in back, and it was bridging two electrodes. And they, when they rebuild this thing, they want to put it back into service for the next 50 years. They don't want to have to worry about it. But with that welding rod in there, that would have caused a serious problem. So he was able to locate it using ultrasound, and it was a good find. Okay, here's a 13.8 kV switch gear yard, and just using our SonoView. Here's the cable here. It's just running from this insulator back to this transformer, and right here in the middle, we picked up some corona activity. We thought, well, that's kind of strange. What's going on there? So it just turned out that it was a little bit of bird caging was happening on the cable, and so on the next shutdown, it wasn't anything serious. It could wait till the next shutdown, but on the next shutdown, they just replaced this length of cable here, and the problem went away. Now, we always want to be perfect, but sometimes we miss something. So again, this is my friend Craig, and he was out doing. He does a lot of polymeric insulation inspections, and here's one that he completely missed. He missed it with infrared, and he missed it with ultrasound. The point being that we don't always get everything right, but when we try to, and these polymeric insulators, they can wear out over time. The elements, weather, and when the insulation material starts to wear out, then water can get into them. And in our climates up here in the north, that can lead to freezing. It can also lead to intense steam buildup when it gets heated. And so he ended up missing one of them, and it turned into a pole fire that caused a lot of problem for the customer. And it's just to show us that we're not always perfect. Here we have corona that he picked up on a lightning arrestor. So again, here's just a digital camera, a digital image, and right down in here, you can see it over here, just a bad connection. There's Craig right there using his acoustic imaging camera. This is supposed to be a video. Let's hope that, yep, there it goes. So he's heard something there. He's just adjusting the sensitivity, and now he's gonna, boom, take a picture. And then he'll put that into his report. Now, what he was inspecting these transformer phases, but what he actually ended up finding was, and it's pretty common apparently, is when you have these lines coming through the brick, that you tend to get these are real prime sources of arcing. So here, or corona, sorry. So you can see right here, that's the image that he captured. He was actually inspecting these, but he was able to isolate that there was a corona fault coming through the brick there. Well, that logo right there tells me that we're at the end of the presentation. So,
Great. Thank you very much,
awesome.
Allan, for the
You're
presentation.
welcome.
Appreciate it. Okay, let's
Yeah.
see. Where is ultrasound testing most useful in a substation, and where does it have trouble?
Oh, great question. So I'd say any kind in a substation, any kind of connection. So the phases on a transformer, anywhere where the high voltage cable is connected to an insulator. These are all prime places where the dielectric material can start to break down and produce what we call surface discharge. So we're really just looking for early stages of corona, which can eventually, over time, degrade the dielectric material down so that it turns from that into tracking and arcing, and it's the arcing that really becomes the destructive element. So I would say any connection. Now, just recently, and I'm saying within the last year, we outfitted Anglo American Steel in Brazil with a system using both a combination of contact and airborne ultrasound sensors to permanently monitor for surface discharge and internal partial discharge on some very enormous transformers, oil filled transformers that have like something like a 2 year reorder lead time. So they are permanently monitoring these. The data is pulled daily back to their control center. So that's another area, is just transformer monitoring.
Can you save the next question is, can you save the inspection results and compare them later to see if the equipment is getting worse?
Yes. So with the first product that I featured, the SDT 340, that is a route-based data collector, and it's got a significant memory capacity inside. So we can set up surveys and routes where when we find an issue, we capture the decibel reading, we capture the time waveform and the spectrum, and that gets logged into the 340 and transferred back to our software. Now, when we go back a month later, we can scan the area again, and we can collect that data again, and now we have a comparison. Well, we actually we need, to me, 2 points is a comparison, 3 points is a trend. So I really think that you need to have three data sets to build any kind of a trend. Now, what's important with airborne ultrasound inspection is that we control our environment. So some of the things that can intensify corona activity are things like temperature and humidity. So if we collected data in the winter time when it's dry versus in the middle of July or August when things are very humid, I'm assuming that my audience is kind of Ontario based, but I could be wrong. But anyways, it doesn't matter where you're based. The point is that if you collect data um, in dry conditions versus humid conditions, the humid conditions tends to intensify the ultrasound. So that needs to be taken into consideration. The other thing you need to take into consideration is the distance that you are from the defect. So, I mean, just think if you and I are having a conversation and we're 100 meters apart, we're going to have to yell. If we move closer 50 meters apart, well, we won't have to yell as loud. And if we're in the same room together, sitting at a table having a coffee, well, we can whisper. So if we're going to trend sound, we need to control the distance that we are between the sound and the sensor from each different reading. I think that makes sense, right?
Right. Okay. How do your tools integrate with other condition monitoring systems?
How do we integrate with other condition monitoring systems? So I wouldn't say that integration so much as they complement. And in electrical inspections, because that's what this presentation is focused on, I would say that ultrasound complements very well what we do with infrared thermography.
Mhm.
Um, when if we were to move away from electrical and talk about mechanical applications, well, ultrasound complements very well what we do with vibration analysis on rotating equipment. So it's more, how does the technology complement than integrate?
Okay, another question here. What are the limitations of using acoustic imaging cameras for substation inspections, especially in noisy industrial environments or during bad weather?
Ah, so there's two elements to that. So I'm going to say the first one, in noisy industrial environments, is not an issue because acoustic imaging cameras are tuned to high frequency sounds, and we can tune the frequencies even higher because we use digital MEM sensors. So we can tune it to 50 or even 60 kilohertz. That completely filters out and eliminates any of the audible noise that you would hear from that noisy industrial environment that you're working in. The second one, weather. Well, acoustic imaging cameras traditionally have They don't have the same IP rating as as my Apple Watch, for example. I'm not going to take my acoustic imaging camera in the shower with me. I can splash water on it because it is somewhat water resistant, but I wouldn't want to. I wouldn't want to be. I wouldn't want to be doing inspections around the mist of Lake Ontario of Niagara Falls, for example. I think that might be one of the limitations.
Sure. Okay. Here, I've got a long question here from Nadeem. We have medium voltage motor, 6.6 kilovolts from this company. We have an issue wherever we grease the bearings, especially DE side temperature goes high, crossing even alarm limit of 80 degrees C. The grease is
Hmm.
manufacturer recommended. We have can't see this. We have something equipment always show normal conditions while actually not. Does your equipment detect over or lesser grease condition? Can you
Mhm.
catch bearing deterioration? Bearings are roller bearings with brass cage.
Absolutely. This is, again, it's outside of the scope of this presentation
Yeah,
because I really just focus on electrical. But
yeah,
if you remember when I was going through the 8 application pillars, one of the ones I touched on was lubrication. And honestly, I'm actually in Seattle today at a reliability conference, and 9 out of the 10 people coming to our exhibit booth are asking us about lubrication of rolling element bearings. And so what I would say is it Nadine, I think you said, what I would say
yeah.
is if you're adding grease to a bearing and the temperature is shooting up, there's a good chance that that drive-in bearing is already in an over lubricated state. Um, but I'd need to have more information. I want to know
Well,
what's the bearing type, what's the rotational speed, and so on and so forth. There's a lot. And are there other assets, other similar assets in the plant where we could do comparisons, or is it just this one troublemaker? But to answer the question though, absolutely, this is the most important application for ultrasonic condition monitoring is to do precision lubrication of rolling element bearings. And if you give Nadine my contact information, we could
I
have a whole different presentation around that.